Good evening. My name is Kimberly Lau. I'm the current chair of the Academic Senate, and I'm so pleased to welcome all of you to the 53rd Faculty Research Lecture at UCSC. It's wonderful to see so many of you here tonight. The Faculty Research Lecture is an institution supported by the academic senates on all 10 campuses of the University of California. Its purpose is to highlight a faculty member's distinguished research record and to provide the campus and the local community with an opportunity to learn more about the honoree's work. The first faculty research lecture was delivered at UC Berkeley in 1918, and UC Santa Cruz initiated its tradition with Maurice Alexander Nathanson's 1967 lecture. Each year, a committee of academic senate faculty from across all 5 academic divisions nominates a professor to present this prestigious lecture based on the overall excellence of their work. This year, the nomination of Professor Lise Getoor was approved by enthusiastic acclamation at the Senate meeting of May 16, 2018. Dr. Getoor's research spans several fields in data science, including machine learning and reasoning under uncertainty, data management, visual analytics, and social network analysis. As you can see from this brief overview, her work is extremely timely, and as the director of the UCSC D3, standing for Data Discovery and Decisions Data Center, she is also particularly concerned with the responsible use of big data. I'll leave the details of her work to Dean Alex Wolf, which he'll present in his introduction, and of course to Dr. Getoor herself. Before then, however, it's my great pleasure to introduce our Chancellor, George Blumenthal.
Good evening, everyone, and thank you all for coming. This event, which is a peer-chosen honor and the highest academic honor we bestow at UCSC, is always a real highlight of the year for me. And it is so because it spotlights research, which is so central to our mission at UC Santa Cruz. At UCSC, research goes hand in hand with excellent teaching. And we are built on a foundation of academic research over the past half a century. And over a time that I've seen UC Santa Cruz grow and evolve from an innovative and pioneering experiment in higher education to a nationally ranked research university. And I'm incredibly proud of that. And it's work of our faculty, people like Lise Getoor, tonight's lecturer, that have gotten us to this place. It really feels amazing that this is our 53rd annual Faculty Research Lecture. And just for the record, while I've been to a lot of them, I haven't been to all of them. It's important to note that research is also what sets the University of California apart from other systems of higher education. It's an engine of discovery that has fueled the Golden State for decades. Importantly, research also satisfies that uniquely human quest for exploration, for knowledge, and for insight. UC Santa Cruz is the home to artists and scientists, philosophers and engineers, astronomers and poets, sociologists and economists. Scholars across all of these disciplines advance our understanding of the world around us. Their contributions enrich us, and they enrich educational experience that we can offer to our students. UC Santa Cruz students get extraordinary opportunities to work side by side with leading scholars, big thinkers who are advancing their disciplines and really transforming their fields. Our professors keep asking important questions, keep writing, and keep sharing their knowledge. Tonight, we get to hear from one of our very best, Lise Getoor, the 2019 Faculty Research Lecturer. I had the immense pleasure of getting to know Lise on an international trip we made a few years ago to South Korea, where I remember that she wowed executives at several Korean companies that we visited. Just as I'm sure she will wow us tonight with her presentation. And here to formally introduce Lisa is Baskin School of Engineering Dean Alex Wolf. Alex?
Thank you, George, and thank you all for coming tonight. I'd like to offer a special thank you to my fellow academic senators for recognizing tonight's speaker. As Dean of the Baskin School of Engineering, one of the many privileges I get is to get acquainted with our remarkable faculty and their very impressive work. And then I get to trumpet how wonderful they are to as many people as I can. So tonight, I could not be more honored to introduce Professor Lise Getoor, a scholar who embodies the definition of world-class faculty. First, though, I'd like to offer a bit of biographical background on Lisa. Lisa is a genuine product of the West Coast. Lisa was born in Seattle and grew up in San Diego. Lisa is also a child of the UC system. Her father was a well-known mathematician on the faculty of UC San Diego. She earned a bachelor's degree in computer science at UC Santa Barbara and a master's at UC Berkeley. And then something went wrong. Somehow she earned a PhD in computer science at Stanford. PhD in hand, Lisa joined the computer science faculty at the University of Maryland in College Park and distinguished herself with her research in, as Kim said, machine learning, reasoning under uncertainty, data management, visual analytics, and social network analysis. In 2013, she returned to her UC roots and joined us here at UC Santa Cruz in the Department of Computer Science. When you hear just some of the ways in which Lisa has distinguished herself, you'll understand why we're so lucky to have recruited her and why we're so proud to have her here with us today. Needless to say, she has been an incredibly successful and highly cited researcher and a highly sought after speaker and lecturer. Lisa is a fellow of the Association for the Advancement of Artificial Intelligence, AAAI. Lisa is the PI for one of only a handful of National Science Foundation Transdisciplinary Research and Principles of Data Science, or TRIPOD's, Phase 1 grants. This grant brings together UC Santa Cruz faculty to develop a unified theory of data science applied to uncertain and heterogeneous graph and network data. She and her colleagues are now hard at work on a Phase 2 proposal, which hopefully will move the work into a larger multi-institutional research setting. Lisa led the establishment of the UC Santa Cruz Data Discovery and Decisions Data Science Research Center, D3, and serves as founding director. D3, among its research activities, works with companies to provide opportunities for collaborations between students, faculty, and industry. But more than her scholarly work, Lisa has been a highly visible national and international leader and advocate. Lisa served as chair of the Computing Research Association's Subcommittee on Data Science and was lead author of a highly influential CRA study on computer science and the emerging field of data science. Lisa serves on the National Academy of Sciences Roundtable on Data Science Education, where the next roundtable discussion is focused on collaborations between industry and academia on data science. Lisa is also a quiet yet exceptionally strong supporter and advocate for women in the data science and machine learning communities, and committed more broadly to mentoring students, junior faculty, and women in STEM. To say the least, Lisa brings great distinction to the Baskin School of Engineering and to UC Santa Cruz, and I'm delighted to see her accomplishments recognized so publicly tonight. So please join me in welcoming the presenter of the 2019 Faculty Research Lecture, Professor Lise Getoor.
All right, well, thank you, George and Alex and Kim, for the really nice introduction, and thanks everybody for helping to make this happen. And thank you guys for coming out in the rain. I'm really happy to see all of you here, and I'm going to be talking about a topic that I think is really important, responsible data science, and I hope by the end of this lecture you will agree with me. Now, as far as my goals in this talk, so I have several. The first one, like any good academic, I am professor. I want to educate you a little bit. I want to also excite you about some of the opportunities in data science. I also want to caution you. And at the end, I want to leave you with some tools, and tools that ideally help you separate some of the kind of reality from hype and vice versa, but also enough background so that you can kind of engage in what I think is going to be a really important emerging area on just what we do as we go forward with data science and more. So I'm going to start at the very beginning. So what is data science? So is it this kind of emerging discipline, or is it just a giant big fad that's going to go away? And I really like this quote that is from Catherine Carson. She's a historian and ethnographer of contemporary science. And what she has to say is, data science is a shimmering concept. No one agrees exactly what it is, but it gets at changes underway that are serious and real. Both in academic disciplines and out there in the world, something is emerging in this space where massive or pervasive data, its computational handling, and its analytic manipulation come together to underwrite inferential conclusions and actions in a datafied world. She goes on to say, whether we're looking at foundational approaches, domain area uses, or contextual implications and entanglements, the intellectual terrain is just starting to get mapped. And however each go forward, there's something irreversible happening. Whatever else happens to the techniques, the questions, or even the disciplines, the data are not going away. And so, as Alex mentioned, I've been involved in a number of these conversations across nationally and internationally around data science, and it is true that there's something emerging happening. Just to give you one example, at UC Berkeley, they have a course, which is their Data Science 8 course. And this is an interesting course. It's designed for freshmen and sophomore students. They don't have to have any computation or statistics background. The most recent edition that was in fall of this past year had 1,300 students, 300 more on the wait list. And the thing that is novel about this is, it's, well, we do this in a lot of our courses, it's grounded in applications, but then a lot of the applications are for the social world. So their goal is that eventually all incoming students will take this class and will then be kind of literate in data science, computational thinking, and statistical thinking, and ethics. Here at Santa Cruz, Abel Rodriguez has led many of the efforts around data science together with folks in CSE and more. So what is interesting as well is, there's a lot of cool things about the course, but for example, the gender ratio in the course is much more equal. So the focus of this talk, however, is on responsible data science. And so in order to ground this work in responsible data science, I'm going to be using a concept of socio-technical systems. So socio-technical systems are a term that comes from the science, technology, and society community. But fundamentally, it gets at this kind of interaction between people and technology. And you'll see throughout the talk, I'm going to return to this as an important component of responsible data science. So in this talk, I have 3 parts. I'm going to give you some basics. And in the basics, what I really hope to do is there's a number of terms that are being used in the media, algorithms and AI and machine learning. I want to unpack these for you. Then I'm going to go over some research. And then I'm going to spend some time going over cautions and things to be aware of. And throughout the talk, what I'd like you to keep in mind is some of the how, when, why, and why not. I am going to try and give you enough of an intuition about how some of these things work that ideally you can have also some understanding of when they might be applicable and also when they might go wrong. So let me get started with that. And let me get started with the most basic piece, which is what is an algorithm? This term is being thrown around by the media quite a bit. And the basic idea is, it's just a kind of recipe for doing something. And people use them all the time. Anytime that you have some kind of task that you need to do, I'm going to bake a cake. I need some ingredients. I have some steps. So I follow those steps and I get a cake out. That's a human algorithm. When the term is used by the media, they're talking about computer algorithms. So I am going to give you a crash course in algorithms, and I'm going to go through 5 different kinds of algorithms, and as I go through them, keep in the back of your mind, what are the different ways these could be used, but what are the different ways that they could potentially go wrong. So, first one, straight line algorithms. Okay, everybody admit it. So how many of you have ever written a computer program? Okay, bravo. So the very first program you probably wrote was a straight line program where you basically just go through, you say some steps. This is an example of one that computes your account balance after you make a withdrawal. Okay. The next kind of algorithm is a rule-based algorithm where you have some sort of conditional, so some sort of if-then. So even in my little code snippet, some of you may have thought, well, it might have been smart if you checked to see if you had enough money in your account before you made the withdrawal. The interesting thing is these are the kinds of programs that are often used for diagnosing things. So here's a little snippet of how you might diagnose what's going wrong with your printer if your printer is not working. And the key thing to note is these kinds of algorithms go by the term expert systems in AI. So these were initially super popular in the 80s, but they're still very popular for detecting problems and debugging things. Those annoying call centers that you call and then route you through things are a form of expert system. Okay, now let's get to a data-driven algorithm. So a data-driven algorithm is something where you have some data coming in, you go through the data, you do some counts, and check how often something occurs. So as an example, here's my, I have some shopping data, and I've counted the number of times someone bought bananas and they bought milk, the number of times they bought bananas and bread, bananas and carrots, and bananas and, whatever it is in that white jar. And then a new customer comes and, they have bananas, and, I'll pick whichever one of those happened most often. Maybe most often it was milk, and I'll say, go down the milk aisle. And now, these kinds of algorithms are often called machine learning algorithms, and this is an example of a recommender system in particular. Now you can get fancier than this, so you can have some statistical model behind this and so on, but the key underlying thing that's done is counting. So keep that in mind when you're thinking about when these will work and when they won't. Another very useful kind of algorithm is a randomized algorithm. So randomized algorithms have some sort of simulated coin flipping involved. And these are super useful for different things. So one of the things they're really useful for is if you're searching very large spaces, it helps. Another thing is if you're doing simulations of distributions in some sort of statistical model, they're useful. And they're also useful if you're designing a game where you want it to be interesting. So the same thing doesn't happen every time you play the game. And then the last algorithm category that I want to go over is deep learning. So how many of you have heard of deep learning? Okay, so deep learning is getting a lot of attention these days. And just at the kind of simplest level, deep learning is all about kind of constructing a super simplified abstract neural network. And they're very good when you have large numbers of input-output pairs of coming up with a compressed representation for them. And so they're good at memorizing large amounts and constructing an abstract representation. The models are considered what's called black box because, just inspecting a neural net, it's really hard to figure out, what exactly it's doing. And there's been some pretty serious issues. There's a ton of examples of deep networks gone wrong. One of the basic first ones came out of Irvine, where they were looking at a deep network that was trained to recognize the difference between huskies and wolves. And so it performed really well on the training data. Then they took some new data, and it didn't do so well on the new data. And it turned out that what the neural net had memorized was all of the wolves had snow in the background, all of the dogs had grass in the background, and that's what it had learned. So a colleague of mine, Rich Karuna, a number of people are kind of advocating caution with these. He has this friends don't let friends use black box models. And I actually think this Wired title gets it. Greedy, brittle, opaque, and shallow, the downsides to deep learning. So I think there's some really cool things that they can do, but there's some cautions, and I'm going to be returning to those in a later part of the talk. So you have just had a crash course in algorithms. You get your gold star and check mark. So now you just had extensive education in data science. I'm now going to turn to talking about research. And in talking, we're going to come back to these algorithms as we go through. In talking about my research, I'm going to return to talking about these kind of socio-technical systems that are complex, connected, heterogeneous, and so on. And one of the things that all of these algorithms, machine learning and data science algorithms typically do is they take this rich structure and they flatten it. So they flatten it into tables where kind of each row in the table is treated independently and atomically. And so they kind of take this kind of cool data and they put it into a table. So what are the issues with that? It turns out that there's actually a bunch of issues. So first off, this flattening oftentimes is making incorrect independence assumptions. Further, the models end up oftentimes not being interpretable. And here, not interpretable in a different way than I'm talking about for deep learning, because oftentimes what you do is you do a lot of feature engineering to transfer that rich graphy structure into the columns in this table. And, then, you wrote some code to do that, you lose the code, it ends up, you don't remember how you got these, very bad. It's not declarative in that way. But the one that I want to emphasize is that it doesn't support collective reasoning. And so collective reasoning is this idea that rather than treat all of the inferences independently, let's model the dependence. And the particular way that we model the dependence, we can use kind of local information about whatever we're trying to make inferences about, but then let's also use the kind of relational structure. And you can use this for prediction. I probably will lapse into talking about prediction, but you can also use it for discovery. So just trying to kind of understand what's going on in your domain or your data. And you can also use it for causal modeling. Causal modeling is important when you actually kind of want to make an intervention. I'm not going to be talking about that here so much, but I'm very interested in causal modeling in networks where there might be interference and so on. So if anybody's interested in that, come talk to me afterwards. So let me go through some examples of this collective reasoning. And I'm going to go through them. They're going to be simple examples, but I hope you'll see kind of the utility of each of them. So the first one is information integration. And information integration is something that happens all the time when you're doing any kind of data science problem where you have these different digital representations for things, and you have to figure out which ones are talking about the same thing. So think about bioinformatics. You have a bunch of articles that are talking about genes. They're referred to different ways. How do I figure out which ones are the same? I have different treatments. How do I figure out which drugs are the same? Or, something like digital humanities, where you have a bunch of text, and maybe you have video, maybe you have images, and again, you're trying to kind of figure out, is this person over here or this place over here the same in these different texts? So, the challenge with all this is typically there's all sorts of noisy clues that you essentially want to piece together. And so I'm going to do a very relevant Santa Cruz example. So this is a collection of documents about the university and talking about our mascot. And the idea is which references refer to the same real-world entity. And I'm going to make use of kind of just in a single document local information. So I'm going to figure out, which things refer to the university, to UC Santa Cruz, and because I figured out those two are the same, then I can figure out the university and the school are the same. I can look at mascot and banana slug. And so this is something that in natural language processing is referred to as co-reference resolution, kind of figuring out all these things that whether they're the same in, say, a single document. But now I can go to a document collection and again do the same kind of reasoning, but reasoning that goes across these different documents to real-world entities. And then I might have another document. This happens to be about Falafel Santa Cruz. I'm talking about the owner, Sam, and I figure out that that Sam is not the same as Sammy. And so there's this kind of figuring out what's the same and figuring out what's different. So this has a number of challenges. One of the biggest challenges is there's tons of uncertainty. I made this seem like, oh, it was totally obvious which one referred to the same thing. Usually, there's a lot more ambiguity, and being able to handle all of that ambiguity is the challenge. And again, I showed it to you for like 4 documents. How do you do this at scale when you're overloaded with digital information for doing this? So that's the first example of collective reasoning. The next one I want to do is collective classification. And collective classification is just the idea that many data science problems, you have a bunch of entities that you're trying to label or classify in some ways. Now, it could be according to some demographic attribute, so it could be according to gender, could be some sort of political persuasion or so on. I'm going to do a slightly more complex example, which is trying to figure out in an online debate different people's positions on a topic. And so I have a debate, people are posting things. Those arrows, the green arrow is I agree with you, the red arrow is that I disagree with you, and the question is, what is their stance? Is it, pro the topic or against the topic? And this is a topic that my former PhD student, Danya Sridhar, who's now doing her postdoc at Columbia, worked on together with Marilyn Walker. Marilyn Walker does tons of work in this space of dialogues. I'm going to be going through a simplified version of this. But again, in order to kind of figure out user stances, I can start off and I can look, just at the document, and I can infer something about maybe the sentiment or some other words that are used in it, what the stance is likely to be. But then the relational information is exactly kind of then using these disagree and agree links to reason about what the stances would be. And I can reason about the stances by saying things like, okay, if someone's pro and someone agrees with them, then the other person is pro. If someone's pro and a person disagrees with them, then that person is likely to be anti. And just like before, I'm, kind of writing this as this logical rule. It's actually going to be uncertain, so it won't always hold, but these are little clues about what the stances might be. So I can go through and make the inferences. Now here, one of the challenges that may have crossed your mind as I described this is, well, what if I didn't want you to figure out my stance? So privacy. So this kind of inference where even if I try and hide my attribute, maybe my demographic attribute, by doing this kind of reasoning, it's oftentimes very easy to infer something. And I've been in a number of conversations around big data and privacy where you kind of say like, oh, the way that we'll make sure you can't disclose this is we'll say you're not allowed to store it. Well, if you're able to infer it with high probability, then that's an important kind of leak. And my former PhD student, Elena Zaliva, who's now an assistant professor at University of Illinois, Chicago, actually way back in 2009, did some interesting work on basically Facebook, looking at the ways that you could figure out demographic attributes through group memberships. And we're kind of used to, oh, your friends tell you something about yourself, but it turns out that group membership tells you even more. And interestingly enough, for group memberships, the group owner had control over that information. You didn't even have control over, who saw this. So this whole topic of privacy, and particularly privacy in technical systems, is really interesting and important to be aware of. The last pattern that I want to talk about is recommendation. And so recommendation is something that I'm sure all you guys are familiar with. A very common thing where you're trying to, recommend some item or give users a ranked list of documents or something. And again, you can use some information. So here's an example. I'm trying to figure out if a user will like an item and which items will the user like. And I can use local information. So if a user's interested in a topic and the item, in this case maybe a news article, is about that topic, then I can say that the user will like that topic. But then I can also use this kind of graphy information. So I can say that, okay, if a user likes an item, another item is similar to that, then the user will like that second item. I can also reason about the similarity between users. So I can say if a user likes an item, there's another user that's similar to that user, then the second user will like that item too. So I can kind of infer all these little triangles. So what's the challenge here? The challenge here is, how do I define the similarity measure? There's not going to be one unique similarity measure to use. There's all kinds of different ways that you can be similar. And part of our work is very much, we're going to allow you to specify a bunch of different ways of doing this and kind of combine them together in a tractable way. So the commonality with all of these is there's some kind of relational structure. There's these complex heterogeneous interdependencies, and there's noise and uncertainty. So my research is all about how you take a more nuanced approach that takes into account these relationships, but at the same time, the context and the probabilistic dependencies. And so I've done work in this space for a long time. I'm going to be telling you about some of our most recent work, which is called Probabilistic Soft Logic, or PSL. And it's a programming language that allows you in an easy and scalable way to, represent these kind of collective inference problems. And the cool thing about it is that it combines, those rule-based algorithms that we saw before with data-driven approaches. It combines logic and probability. It combines both hard and soft constraints, so hard constraints that have to be satisfied, soft constraints which you'd like to have satisfied, and fundamentally it ends up combining knowledge and data in a really interesting way. And so at this point, I have to acknowledge my awesome group of students. This is links for Lisa's inquisitive students. I have some of them around in the audience, I think. So they're awesome. They're the ones that make being a professor awesome. That's the best part. So thank you guys. So PSL is this probabilistic programming language for collective reasoning. And the way it's encoded is we have some weighted rules. Then we have some data together with the rules. And the cool thing is it then defines a probability distribution over the collective outcomes. And a PSL program, this is an example of a PSL program for that stance example from before. So it's pretty simple to write, it's pretty interpretable. And it basically kind of takes, this is a program, you have some data, and it's instantiated into a particular kind of distribution. And the distribution is a particular form of Markov random field. So it's a hinge loss Markov random field. You know, if I was in a more technical setting, I would go off on a deep dive here for like an hour telling you all about this. But since I'm not, I'll have to give you the high level. The high level that's really cool is it's taking logical inference, which is known to be intractable, and mapping it to convex optimization. And the neat thing about this was very much work of my former PhD student, Stephen Bach, who's now an assistant professor at Brown, and my former postdoc, who's now an assistant professor at Virginia Tech, where we looked at those randomized algorithms, some results from there, some results from machine learning, graphical models, certain kinds of relaxations for them, and soft logic, so something that's in the AI world where you have, rather than have Boolean values that are true, false, you have, they can be interpreted either as degree of truth or similarity. We were able to show that there was one formalism that there was equivalent optimization under these three different interpretations, and that it ended up giving this scalable way of doing inference in these large models. And so this is kind of really cool whenever you get something that under three quite different interpretations, you end up with the same optimization. I think that shows that there's something fundamental there. There's still a lot more work to do. You know, if this excites any of you, come talk to me because, yeah, there's lots more things we could do from here. So, PSL in a nutshell, it's able to do inference really fast. You can make it even faster by using kind of state-of-the-art optimization techniques, distributed processing. It turns out there's a lot of fine-grained local parallelism. I'm not talking about it here, but you can learn the rules, you can learn the weights for the rules. You can also deal with latent variables, which I'm going to give an example of in just a minute. It combines data and knowledge in this interesting way that ends up giving you these models which are much more interpretable. And the cool thing is, you know, it's open source, code, data, tutorials are all available online. And if any of you are interested in using it, we like to help people, so come talk to us. Let me go over now 2 examples. that are a little bit more complex than the ones we went over so far. The first was an example where we used PSL models to detect cyberbullying. And so we were able to not only kind of look at different messages and infer, when the messages were bullying messages, but we were also kind of trying to tease out the social structure. So what are the different roles? And then also discover what are the different kinds of attack types. And the PSL program for this, this is work by Sabina Tompkins. So she was a former PhD student who's now doing a postdoc at Harvard, who just graduated from here last year. This is the program. I won't make you read that, but if you want the code, it's here. And she demonstrated it on some. This was cyberbullying and Twitter, which you can imagine that has a lot of complexities. And, you see this tweet, is it really a bullying tweet or not? And one of the things we were able to show that modeling that uncertainty in the label, actually you could do a better job from modeling the uncertainty. She also was able to kind of uncover some evidence of certain kinds of power dynamics and found certain things like what are the most common attack types and so on. So this is one example. Another example in the social domain was some work by my former postdoc, Bert Wong, that I mentioned before on inferring trust, social trust. So here I have these individuals, and the green links are that they trust one another, the red links are that they distrust each other. And there's actually, two very well-known different theories of trust in social psychology. One is called the structural balance. This is the idea that kind of a friend of a friend is a friend, an enemy of an enemy is my friend, and so on. So it gives like all these combinations of trust and distrust and says, which ones are stable. And the theory says you're going to go towards this stable configuration. A competing theory is the social status theory, and this is much more about hierarchical relationships. So the idea that I trust people that have more expertise than me or that are higher in the hierarchy, and I distrust the people below me. And the interesting thing is for this, it will give you kind of different combinations of trust and distrust links. And so what we could do is we could build a PSL model for both of these, the PSL balance and PSL trust. We compared it to a baseline and what was at the time two state-of-the-art methods. And this is for predicting distrust links, which is actually really hard to do. We ended up, both our models did better than state-of-the-art methods. But now, the thing that we did from here, I think is really cool. We then added in a psychological variable, so a latent variable that talks about how trusting or how trustworthy an individual is. And adding this into the model ended up boosting performance significantly. And I think this happens a lot in these kinds of models, kind of judicious insertion of these latent variables, and then when you're able to have some interpretation for them, it's very interesting. So the cool thing is to then go back and look at the organization and try and say, like, oh, what is it about the place where the balance model was working? What is it about the part where the status was working, and can I say more? We've done a lot of other projects, just to mention some work by Artie Ramesh, a former PhD student who's now a professor, assistant professor at SUNY Binghamton. It's done work with MOOCs, so looking at engagement and different kinds of social behavioral effects in MOOCs. P. Kuki, who just recently graduated, has done a bunch in recommendation, but also explanations, like why did you give me that recommendation? And Jay Pujara, who's now an assistant professor at USC, did a lot of work in knowledge graphs. And this is kind of going a little bit beyond this information integration that I talked about so far, where you're trying to kind of extract out these knowledge structures from text or other digital information. So that was about research. And I am very, very happy to talk more about it. I want to go into talking about some cautions. And for the cautions, what can go wrong? Go back to those little algorithms that I gave at the beginning and kind of think about some of the things that can go wrong. It turns out a lot can go wrong. I'm going to go through some examples that I've gotten from my colleagues. I'm actually going to be teaching a course in this next year, so if you have other examples, send them my way. These have been getting a lot of press, and I'm just going over a couple of these. So the first example comes from Amazon, and Amazon, this was covered by Bloomberg in 2016. They built a tool to decide where they should offer same-day delivery. So it's a Prime service. And they trained it on users' buying history, income, and location. And focus right now on just the left side of this slide. So the part in gray shows the part of Atlanta that did get the service. So the northern part did get the service. This is Chicago. Everybody except the south side got it. And this is Boston. Everybody except Roxbury got it. And what happens to be true about these assignments is, predominantly white areas got the service and predominantly African American areas did not get the service. And so essentially what they did was they built a tool. The tool did not explicitly use race, but not surprising, given those attributes, it basically came up with a digital redlining algorithm. And so they got a lot of flack, and everybody in these areas now is receiving the service. That's one example. Another Amazon example is that they built a tool to recommend resumes. And guess what? They trained it on their own resumes. And their own resumes were predominantly male. And guess what? The algorithm ended up showing a gender bias. So Amazon's not alone. Here's some Google examples. As a matter of fact, Science and Justice is going to have a speaker in March that's going to be talking about bias in search results. So I'm going to cover a couple different Google examples. One of them is in their Smart Compose, where they are filling in pronouns. It turns out that, you type in CEO, you get out and fill in the pronouns, they're all going to be male pronouns. This is Google Translate. You take a language like English that is gendered, and you say, she is a doctor, he is a nurse. You translate it into Turkish, not gendered. You translate it back into English, you get, he is a doctor and she is a nurse. So, but probably the example that has gotten the most attention is around recidivism prediction. So how many of you are familiar with this story, this ProPublica story? Okay, so not a lot. So this is really interesting. So, and I'm not going to be able to do justice to it, all of the nuances, but basically there's an algorithm that is being used widely in the criminal justice system for pretrial, bail, and sentencing, where the algorithm is supposed to predict the defendant's likelihood of committing a crime. Well, it turns out they were able to show in a particular county that what was happening was there was strong racial disparity in the effects. So first off, false positive, where you say someone is high risk, but they're not high risk. This happened twice as often to African Americans as to whites. Then false negatives, where you say they're low risk, but they actually do go on to commit a crime. That kind of error happened almost twice as often for white defendants. So the issue here is over-predicting recidivism for African Americans and under-predicting recidivism for whites. So what went wrong? Okay, so a bunch of things that went wrong. So one of the things that went wrong in all of these examples is biased data. So if you have input to your system that's biased, whether the bias is coming from selection bias, institution bias, or societal bias, then the output is going to be biased. And so this is famous computer science phrase, garbage in, garbage out. If you give it bad data, you're going to get out bad results. Now, it turns out that there's a lot of other kinds of biases in addition to these that are important to take into account. And one of them is automation bias. And this is a well-known effect where people have this habit of, the algorithm told me to do it, and they trust the algorithm too much. So this is a serious issue. Sometimes it said you trust the algorithm, sometimes, it's a hard decision, and so, the algorithm made me do it. In the case of the recidivism prediction, it's actually even worse, because in a number of states, if the judge disagrees with the algorithm, then they have to write a report explaining why. And so that puts like an additional overhead. And all of this leads to what's referred to as algorithmic discrimination. So the idea that algorithms can amplify bias, which we just saw, but they can also operationalize it in a way that it's applied much more widely than, from just a biased individual. And then it also legitimizes it, so that it's given too much credence. And so, not surprisingly, people have been, this has become a very active area of research. So as an example, here are the, in 2011, there were hardly any papers about machine learning and fairness. This is from a tutorial by Salon Barkas and Moritz Hart. By 2017, there were a ton of them. There's several workshops, and there's now actually an ACM conference on fairness, accountability, and transparency, where it's specifically trying to bring together technologists and policy folks and practitioners to talk about these issues. So there's been a huge surge in academic research. Not surprisingly, there's been some criticism of that research. So there's been a healthy amount of critiquing these kind of technological fixes. It's like, I'm going to have my machine learning algorithm, and then I'm going to put on an ethics box at the end to fix everything. The cool thing is, I think there's starting to be some real collaborations where through some discovery of what was happening on the technical side, together with some interpretation of that on the social side, kind of new, interesting things are coming out. And I really like this quote by Bill Howe at UW. He says, responsibility means going beyond technical or technocratic solutions to also involve substantive debate about ethics, values, and competing interest. How is ethical expertise defined? Who gets to be at the table? What are the limits of certain kinds of solutions? So this is what's happening in academia. Turns out there's things that are happening in the real world too. This is the first law in New York on automated decision systems, and there's a number of other efforts. So I'm happy about this. There's a lot of energy and research that's happening here. I want to talk about what else can go wrong and what are the things that can go wrong that I don't think are receiving the attention that they deserve. So first is just poor quality. Just like there's bad data, there's bad algorithms. You know, if you look at that first line on that ProPublica thing, you know, this thing only had 61% accuracy. You know, that's barely better than flipping a coin. You know, we should not be using these things in these settings. The second one is magical thinking. So I think there's a lot of writing right now about machine learning and AI and all these things that it can do that is overinflated. And so you really need to question the capabilities. And I hope I'm giving you some of the tools that will help you be a little bit more skeptical of some of the claims. And to unpack why you should be skeptical, I'm going to go over one technical problem, which is the frame problem. And this is the just basic idea, which, I mean, you should have seen from the examples that I gave. You know, these are really crude models. So they're going to make simplifying assumptions so they can only take into account some kind of limited amount of information, and from that limited amount of information, they can make big mistakes. So AI and machine learning methods can work well, but usually in very kind of constrained settings. And this is what's referred to as weak AI or narrow AI. The fourth thing that can go wrong is values. So all of these algorithms at their heart are optimizing some metric. There's a question of who supplied the metric, you know, who gets to decide it, whose values are encoded in it, and so on. Another issue is just bad code. So just like we had bad data and bad models, you can have bad code. And so the whole area of software engineering, you know, our dean, that's one of his research areas of software engineering, is all about, you know, how do you ensure that code doesn't have mistakes in it? Now, when you're going to data science algorithms and data-driven algorithms, how do you ensure things, statistical properties like, and good science practice about reproducibility, generalizability, transparency, and interpretability. You know, these are all important. And the last one that I want to mention is taking into account that algorithms can actually shape people. So again, going back to our socio-technical system, we have people interacting with technology and algorithms. Sometimes people adjust and adapt their behaviors in response to algorithms. You can probably think of some that you've done yourself. Sometimes it's in benign ways, sometimes it's in adversarial ways, and sometimes it's just in unintended ways. And we really need to think more carefully about the potential impacts on people's behaviors, in particular their agency and their autonomy, as we design ever more complex adaptive systems. So in closing, I have a couple more things that I'd like to go over. First off, I'm going to give some advice. My students and colleagues will attest to the fact that I love to give advice. So first off, advice to computer scientists. Some things to keep in mind. First off, data is not objective. It has biases, historical context, and more. This is something that social scientists, statisticians, they're totally well versed in. This is something that's not as commonly taught in computer science or emphasized in computer science. Technology is not neutral. They have values baked in. It's important to think about them. And there's a moral imperative to understand the domains in which your work is being applied and consider the domains to which your work could be applied. There's a ton of new research that needs to be done to deal with these incomplete, uncertain, biased socio-technical systems. And finally, we really need to educate people. So we need to educate people about some of the limitations of algorithms, machine learning, AI, and more. Okay, so advice for collaborating with computer scientists. Some things to keep in mind. One of the things is we love abstractions and simplifications. And I think if you're a humanist and so on, this is kind of a totally different way of thinking where, humanists, you're about the specific, the context, so on. And so oftentimes kind of keeping this in mind that you have kind of different mindsets is actually useful. We really like logic. So we like zeros and ones, trues and false, black and white. So that's another useful thing to keep in mind. We don't always have the greatest people skills. So yes, there are more introverts and Asperger's and other things among computer scientists and engineers. It's useful to keep this in mind. I remember the first student that I had that had Asperger's. Once I kind of figured out that that was the issue, it's like it made everything much, much easier to deal with. So we're not typically trained in ethics yet. So there is a huge surge of interest across the country nationally about ethics training, and ethics training that's not just a Band-Aid, here's your ethics class, but that really goes throughout the curriculum. And like many, we want to make the world a better place. So, we want to collaborate with folks in doing this. So, what is responsible data science? I've kind of emphasized the literacy aspects of it, and computational literacy, statistical literacy, ethics literacy, justice, domain literacy. That is also data science for social good. So this is also an active area where a number of universities and other organizations are developing these programs around data science for social good. Raed Ghani at the University of Chicago was one of the first people to do this, and I've had him come to speak at campus a number of times. One of the things I find interesting is that I think the most interesting ethics discussions are coming out of the folks that are working in this space. Some of the deepest discussions that I've heard about ethics are folks coming from here. And so responsibility means working on these hard societal problems. So we can use data science to discover the bias, to discover the injustices. We can look at hard problems like homelessness. And we can look at things like education justice. This is something that Rebecca London and Radha Gawa are doing some cool work where they're combining together education outcomes together with juvenile justice and social programs to understand, what's happening, especially to kind of marginalized populations. Some work by my former PhD student combining two hard things, environment and human trafficking, and looking at what the impacts are. So I think we have a choice. We have a choice about, we can build these socio-technical systems, these kind of dystopian ones where, we automate bias and they surveil us and they make us angry and unhappy. Or we can build these kind of utopian ones where, we collaborate and we do collective actions and we help make the world a better place. And I think it's our choice. We really need to be thinking about, in bigger picture, which are we going to choose? So, returning to my goals, hopefully teach, excite, caution, and give you some tools. In terms of takeaways, this literacy aspect of computational literacy, statistical literacy, ethics, justice, and then a process-oriented view towards designing and critiquing the systems that we're building. And then to do this, we really need to collaborate. We need to collaborate across, engineering and humanities, social science, art, education, and, what better place to do this? UC Santa Cruz. We have strength in all these areas. So let's work together. So, thank you.
Thank you, Lisa. I'm reminded of something my mother always said to me, just because you can doesn't mean you should, which seems to be, kind of a theme here. And that thoughtfulness that you're bringing to it is, I think, just incredibly important. And what it's also important is it's not just about the technology, but it's about the social context that surrounds the technology. So as you said, UC Santa Cruz is a wonderful place to explore those questions. And speaking of questions, we have time for some. So I think there are some runners.
So this is not my area and a naive question. I'm right down here in front of you. Okay.
Thank you.
So the algorithms that look at Facebook posts or Twitter messages, is the core data just individual words? Are they really just doing word counts and associations, or can it do something more sophisticated, like the meaning of a word in a sentence?
Okay, so the question was about, so we got it on the mic, so I don't have to repeat it, right? Okay, good. And FYI, I wanted to put up some resources. So resources. So first off, I have to do my sign my disclaimer for Facebook or Twitter. So I'm gonna answer. Hopefully, you could see even from what I was saying that just looking at the text, you can do a surprising amount. So text would just be the word counts. But looking at the relational structure, so who liked things, who's friends with who, and other kinds of attributes, that's something that leaks a lot of information. In terms of inferring additional meaning, yes, there are techniques for trying to infer meaning from text. Sometimes that's grounded in some ways, and sometimes it's not so well grounded. Kind of a separate topic, though, because I think that part of it is like, how much do they know about us? Might be behind it. One of the things that they do is they aggregate a lot of external information, and that external information is something that gives a ton of semantics and so on. So it's really through the kind of combination of these things. Although I will admit that when I've gone to talk, for example, to Facebook, they say that they're not doing a lot of graph inferences. A lot of what they're doing is kind of pretty basic. Other questions?
So in one of your last slides, you showed the picture of the utopia and the dystopia, and you said that we can choose which one we have, but do we really have that ability, or is it out of our hands? You know, this data is external, like you said.
So, first off, I think it is important that we need to think beyond just the technology to understand important concepts, economic concepts, political concepts, social concepts, psychological concepts, to understand where we can affect change and where we can affect it most effectively. I do think that right now we're on the cusp of an opportunity for significant changes. And so, yes, now is a time where, especially around privacy, there's a changing feel to the debate, and participate in it. It's really, really, really important. And then also think of how addictive you are to your little devices, and then try and change some of your own behaviors, which you do have control over.
Okay. Lisa, first, thank you very much for your talk. I don't know how many in the room will know Hannah Arendt, or if you know her work, but she has this very wonderful, a lot of us in the humanities and social sciences, I think, are thinking with her these days. But one of the reasons she wrote a book called The Human Condition, and in that she opens with her worries about the rise of the mathematical sciences and how they might lead to a world in which we could no longer speak and talk about that which we do. And what I love about what you've done here is that you have done the work to speak about that which you do, which can be very technical, but you've made it into a language that we can share and talk about. And so I just want to say that I really appreciate it. I now have 5 different versions of algorithms to work with now. I used to only have one. And I used to code back when it was BASIC in the 1980s. I don't know how many people had that experience, but I want to go to, you're raising these, Arendt alerted us to these issues a long time ago, but they're coming home to really roost right now, and you've presented all these wonderful examples of that. And the question that we're getting to at the end is, how do we change? And this last question was, is it just that we choose? And that, yes, there's an agency part of this, we can choose, but who's the we and how are we going to choose becomes the really hard bit. So I want to go back to a point in your talk where you talk about there is a moral imperative for engineers to think about how what they're doing is going to play out. And I thought this was in actual situations. I'm not quite sure how you phrased it. It was something like that. You said there's a moral imperative. So first of all, I'm interested in how you ground the moral imperative, but secondly, I want to know how you turn the moral imperative into a practical endeavor. And that, if we think about, and I think universities are really important sites for this, because what are we doing other than training the next generation of scientists and engineers? So how pedagogically do we change? And what do you see as some of the pedagogical challenges in engineering schools? What do you see being tried? What do you think is promising? What do you think can happen here? So, easy question.
This is what I love about the STS kinds of questions. So, big question, awesome, and this is why I love being able to talk with folks like you around UC Santa Cruz on these topics. And first off, I think that it's very interesting. A lot of the work in socio-technical systems from, 2 decades ago, I think is all super, super, super relevant now. And this is something that I've been a participant in, being a technologist, talking to humanists about some of the concepts. And we just struggle with the language. Like I know when talking to you when I first got here and talking to Rod about justice, I was like, justice, yes, justice sounds good. Of course I like justice. And then it's like, in the past few years, kind of reading up more, it's like I realized like there's a whole friggin' iceberg of meaning behind it. And right now, around ethics and technology, a number of folks have said they feel like there's a renaissance that's emerging. That renaissance is nascent right now, and a lot of it is, we don't always have the language yet for talking about hard issues. I've been fortunate enough that I've had very patient, some economists kind of explaining to me all these different structures, and philosophers explaining things, and so kind of learning about those. I do see the conversations that even as short as 3 years ago seem like Band-Aids have gone much deeper. And so I see progress, but it requires this kind of respect. And the respect that goes across, yes, I'm willing to explain the complexities of these structures. Where are the places where you can have practical impact? If I had to rank them, where would I look at them, and so on. And what are the concepts that need to be, like if you are trying to train folks, going beyond just saying like, there's Kant and there's utilitarianism, you need something deeper than that. And that deeper thing comes from understanding social science more, so understanding, I think, economics, power, and how that fits in, understanding, political science, understanding sociology, understanding psychology, and more are important in that. And yeah, let's work together on this.
Lisa, I would like to ask you a question. I think I'm quite impressed, because I think it's the first data science talk I've ever heard that did not include the phrase big data. Anybody notice that? But still, I mean, there is...
It used to be very large data before they went to big data.
Now it's big data. But big data, to me, there is an important sense in which it's something to be considered, because we think that bringing information together is going to provide us with data that will feed these models with better information, or at least more information, allow us to make larger decisions that consider more factors. But big data also has the implication of a concentration, and of a concentration of power and of knowledge. And this kind of gets at an earlier question, because that concentration then becomes something that's harder to work against. So do you have any thoughts about how to deal with that aspect of the data science question, this collecting and collocating and encapsulating of large amounts of data that actually drive this whole socio-technical enterprise?
No, that's a very interesting question. And there's multiple levels to answer it at. So, one of the important concerns is, yes, there is a concentration of power due to, a very small number of players having a lot of data. That's beyond a big data science issue.
Yeah.
And that's really important, probably the most important thing. Then the other piece, though, is that hopefully came across in my talk is I don't like things to be purely data-driven. So there's data-driven, but then, I have some knowledge. I have some theory about the way the world works. I want to have a way of kind of representing that as well and kind of marrying the two. And so I didn't emphasize big data in part because I like to operate, I did say we're scalable. And by the way, we do the largest graphical models that anybody does. Even Google's impressed with how big our graphical models are. Yes. But I think this idea that just, big data is going to solve the problem. Certain things are not big data problems. And, since I'm interested in data science for social good, a lot of those problems are not big data issues for a variety of reasons.
Could I ask one question?
Yeah, I think we have time for one more question.
Okay, lovely. I think there's a very timeless, natural trade-off between keeping track and... Oh, yeah.
What?
I'm over here. Hi.
Oh, thanks.
Hi. No, thank you so much for talking to us. I just wanted to ask about the natural trade-off between keeping track of those ethical concerns and implications of other people using your work and progress. I think it's really hard to, try to model, how could this, affect other people in a very negative way while also trying to make progress, right? There's only so many hours in the day, and there's that trade-off. And I was wondering, is there this sliding scale of maybe prioritizing certain ethical implications that we cannot, put aside for the time being to make progress? There are certain, this is where the language comes into play. I don't have the language to describe the ethical implications, but is there a way to balance both? Because I feel like they're at odds with one another, to be very conscientious of your work and wanting to do things quickly so that they can have a very positive impact, potentially. Does that make sense?
I think if I'm interpreting your question the way that you intend, then my answer would be, no, now we need to kind of think through the ethics, and that we can't just kind of throw something out. Actually, so Catherine Carson, the quote that I gave at the very beginning, she has another great, it's an extract from a Twitter stream that's talking about data scientists and basically making an analogy to atomic physics and saying we basically released all these things and we don't even know the impact of them, and just we're in a giant experiment. We're going to see what happens. So I think it's important to not delay.
Yeah.
looking
So you
at
think
them.
we can do both? We can make progress and have a positive impact, and also be aware of all the ethical implications of our work as best as we can. Like, you think we can do both?
Well, and this is the why you want to think of it as a process. So it's a process where you design, you critique, and you build. So it's not just a
one after the other. Yes, absolutely. It should be in tandem. Thank you.
Okay. Well, at this point, I think we need to close. We invite you to have some refreshments upstairs immediately through those doors. But I also want to once again thank Lisa for an incredibly stimulating conversation, and to thank her for her work here at UC Santa Cruz.
Thank you.